Introduction of VFD. VFD stands for Variable Frequency Drive, which is an electronic device used to control the speed of an electric motor. A VFD works by adjusting the frequency of the electrical power supplied to the motor. By changing the frequency, the VFD can control the rotational speed of the motor. VFDs can also control the torque and direction of the motor, making them versatile and widely used in various applications. VFDs are commonly used in HVAC systems, pumps, conveyors, and other industrial applications where precise control of motor speed is required. They can provide energy savings by reducing the power consumption of the motor when less power is needed. VFDs can also prolong the lifespan of the motor by reducing wear and tear caused by excessive speed or frequent starting and stopping. VFDs come in various sizes and types, ranging from small units for home appliances to large industrial units for heavy machinery. They typically consist of a rectifier, a DC bus, an inverter, and a control circuit. The rectifier converts the incoming AC power to DC power, which is stored in the DC bus. The inverter converts the DC power back to AC power with variable frequency and voltage, which is then supplied to the motor. The control circuit adjusts the frequency and voltage output based on the input signals from sensors and other feedback devices. Overall, VFDs provide a versatile and efficient means of controlling the speed and performance of electric motors, making them a valuable tool for many industries. Here is a more detailed description of the parts that make up a typical VFD. Rectifier. The rectifier is the first component in a VFD, and it is responsible for converting the incoming AC power supply into a DC voltage. The rectifier typically consists of a set of diodes arranged in a bridge configuration. The resulting DC voltage is used to power the inverter section of the VFD. DC bus. The DC bus is a capacitor or a set of capacitors that store the DC voltage from the rectifier section. The DC bus helps to smooth out any fluctuations in the DC voltage output, ensuring a constant and steady supply of voltage to the inverter section. Inverter. The inverter section of the VFD is responsible for converting the DC voltage from the DC bus into an AC voltage with a variable frequency and voltage. The inverter typically consists of a set of transistors or insulated gate bipolar transistors, IGBTs, that switch on and off rapidly to create the AC output voltage. The frequency and voltage output of the inverter can be controlled by the VFD's control circuit. Control circuit. The control circuit is the brain of the VFD, and it is responsible for monitoring the input signals from sensors and other feedback devices and adjusting the frequency and voltage output of the inverter section to control the speed and torque of the motor. The control circuit typically consists of a microprocessor, memory, and input/output (I/O) modules. Display. The display is a user interface that allows the operator to monitor and control the VFD's operation. The display typically shows information such as the motor speed, input voltage, output voltage, and fault codes. The operator can use the display to adjust the VFD settings and troubleshoot any issues that arise. Cooling system. The cooling system is an essential part of the VFD, as it helps to dissipate the heat generated by the rectifier, DC bus, and inverter sections. The cooling system can consist of fans, heat sinks, and other components that help to maintain a safe operating temperature for the VFD. These are the primary parts that make up a typical VFD. Depending on the specific application and manufacturer, additional components may be added to the VFD to enhance its performance and reliability. There are different types of VFDs available that are designed for specific functions and applications. Some of the common types of VFDs include AC VFDs. AC VFDs are the most common type of VFD and are used to control the speed of AC induction motors. These VFDs are typically used in applications such as fans, pumps, and conveyors. DC VFDs. DC VFDs are used to control the speed of DC motors. These VFDs are commonly used in applications such as cranes, elevators, and hoists. Servo VFDs. Servo VFDs are designed for precise motion control applications such as robotics, CNC machines, and high-speed printing presses. These VFDs use feedback devices such as encoders to provide accurate position and speed control. Vector VFDs are used in applications that require high torque at low speeds, such as mixers and extruders. These VFDs use sophisticated algorithms to control the motor's current and voltage, providing precise torque control. Multi-level VFDs are used in high-power applications where high efficiency and low harmonic distortion are critical. These VFDs use multiple power semiconductors to generate a high-quality output waveform, reducing energy consumption and improving the motor's lifespan. Regenerative VFDs are used in applications where the motor generates excess energy during deceleration or braking. These VFDs can capture and return this energy to the power grid, reducing energy consumption and improving overall efficiency. Each type of VFD has unique features and benefits that make them suitable for specific applications. When selecting a VFD, it is essential to consider the application's requirements, such as motor type, load characteristics, and control requirements, to ensure the VFD's optimal performance and reliability.